I'm here at the physics department at McGill University in Montreal, and I'm about to get a tour of the Rutherford Museum. So Ernest Rutherford was a professor here in the early 1900s, and they apparently have a lot of the tools and experiments that he actually used back then to discover things like the decay of radiation, other work that led up to the discovery of the nucleus.
Except Rutherford died in 1937, even before he died, never believed in the usefulness of nuclear energy. He couldn't talk about nuclear energy at McGill, but at time, because he said anybody who believes in usefulness of nuclear energy is talking moonshine. Why? Because at the time, the people who did some research on that could never find a way to speed up the process. They knew that uranium will decay, thorium will decay. They knew that in decaying it produces heat. But like I say, you put a ton of uranium in your basement, that's not enough to heat your house. So these two lead bricks, because this is sitting in water.
Okay.
Sinking in water. You have two vases that are sealed. Okay? Connected with the contact a U-tube in which you put the liquid. Okay? So here you put a radioactive source. You put radium, in fact, for example. The small cylinder here is just have gamma rays. The first experiment did that know this cylinder didn't exist, and people complain and say, what about gamma rays? So they put these lead blocks of gamma rays. So now, the radium will decay, producing heat, some heat. Since there's no place to go, it's sealed, what will happen is that, okay, some of the heat will go to the wall here, but the first order, the air will be warm up in the vase. If the air is warming up in the vase, it will expand. If it expands, the only place to go is to push the liquid. On the other side, you have exactly the same setup. Instead of putting a radioactive sources here, you put a heating element connected to a battery and a rheostat and a variable resistance. And you adjust the variable resistance to adjust the power in the resistance. And you can adjust the power till you establish the liquid.
Okay.
So if you do that, you know.
Oh, so now you know that's
you
interesting.
know the power here because you can calculate the power here, knowing the current and all that. And if you establish, means the power here is equal to the power there.
Wow.
So it's very simple. Even if you lose 90%, as long as 90% on both sides, it's okay. But he proved basically that he argued that this is a million times more powerful than chemical reaction. He still didn't believe the usefulness of this power because he could not find a way to speed up the process. In fact, the speeding up of the process came in 1939 when Otto discovered fission. Fission is the trick. First fission comes from separation of nucleus, which means a lot of power, but it's not the main thing. The main thing is that when you do fission, normally there's emission of some neutrons. And you can use these neutrons to induce the next fission on the next atom beside it. And like I say, if you're not have for the effect that you have two fission per on average, because sometimes it's 0, sometimes it's 4. For each fissionless nucleus, you produce 2 neutrons. It can produce a nuclear bomb, a nuclear reactor. If instead of that, the probability to emit a neutron would be only 0.5, you would never heard about nuclear power. And in this tube, you have 3 electrodes, A, B, C. Okay. A tube itself needs only 1 electrode, but they have 3. And you inject the emanation. In the chamber, the emanation will decay, emit alpha particle. You put a voltage with a battery between the central electrode and the tube, so which means you have electric field inside the tube, which means that the positive alpha particle will go toward the negative electrode. What's left behind, which is the negative atom, will go toward the positive electrode. Yeah, the alpha go one way, the atom go the other way, which means the displacement of charge versus the current. That's the division of current, which you can measure using an electroscope. Here you use what's called a quadrant electroscope. In fact, it's like a voltmeter. You measure basically a current. What Rutherford and Soddy found out is the following. If you do that, see here the emanation will decay, producing a current. Then you push the emanation, goes here, goes here. Here you measure another current, but less than here because some of it has decay here. and you keep pushing, he measures another current, but less than E, but something that's decay here. Then it goes out and go to space. So the idea is that he had a setup. In fact, you can inject dissemination at a fixed rate. So many cc per second. And in doing that, they found out that whatever you do, you always have that the current here divided by the current there is equal to current there divided by the current there. If you arrange it to be 1/2 life from here to there, it means here you measure 1, here you measure 1/2, here you measure 1/2 of 1/2, you measure 1/4. If you go very fast, they are more equal. So it could be 1 here, 0.9 here, and 0.9 times 0.9, 0.81 here. Or if you go very slow, they decay more. Okay, but you always have that A over B equal B over C.
And how do you mean to force it through there? It was a gas?
It was a gas. It was emanations a gas.
Okay.
Today we know it's radon. Didn't know about radon at the time.
Okay.
It's a radioactive gas that they mix. It's not pure gas. It's a mixture with air. From that, they discover basically the mathematics of the low radioactivity, this idea of half-life. I told you Rutherford found out there's 2 types of radioactivity, alpha and beta. They knew that beta were electrons, that Thomson discovered, but alpha, for a while they thought about alpha was just a radiation, like X-ray. Today when it's a particle, didn't know that at the time. Rutherford wanted to know what's an alpha. So he did a couple experiments all related to that. For example, this one, the first one he did, he used a source of radium that he got from Marie Curie. Marie Curie discovered radium in 1898, that gave her a Nobel Prize. And then she distributed, she was sophisticated, but she sent around the world to colleagues, basically, some example. So Rutherford had some radium. So he used radium. Radium emit, we know it's alpha particle, emit alpha radiation. You send the radiation to what's called a gold leaf electroscope. I don't know if you know what a gold leaf electroscope is. It's very very thin sheet of gold. If you charge them, they repel each other. And if the discharge with gravity will bring them back. So you saw that radium can charge a gold electroscope, but to find out if it's really a charged particle, you put in between what it's called parallel brass plate. I call it a collimator. There's 3 examples of it here. So basically you have a set of plates separated by maybe 0.5 millimeter. And you put that in a magnetic field. So if you have a charged particle, you put a magnetic field, charged particle will be bending. They will not go through, basically. And that's what they observed, that with magnetic field, you have a reduction in the charge on gold electroscope because the particles are bending, which is a demonstration that it's a charged particle.
Yes.
Not such radiation. In fact, a more interesting experiment is this one here. It's very similar to that, but he wanted to know the charge and the mass of this alpha particle. So basically, to do that, you take only one system of plate. You have 2 plates here separated by maybe 0.5 millimeter. Below it, you put a source. So you have 2 plates. The alpha particle will go straight up and go through, and then impress a film that you put in the support at the top. And if you look at the data here, you can realize on the right hand side here, you basically have 1 line, which is the alpha particle impressing the film. On the left hand side, you have 2 lines. In fact, that's what happened if you put electric field between the 2 plates. The 2 plates insulated, you can put electric field. The particle, instead of going straight up, they will bend a little bit.
Okay.
Which means they will get to the left or to the right, depending on the direction of the field. This is why you have 2 lines. This is one for one direction, one for the other direction. And he put up, this is corresponding to 300 volts. In fact, there was no power supply at the time, so they used batteries. So to get 300 volts, you need 200 batteries. So there are 1.5 volt per battery. And but the bending depends. In fact, he did 2 experiments. This is one explained, the electric field. He did the similar experiment with magnetic field. It's putting a magnet. If your particle go up, in the magnetic field, it bends to the right or the left, depending on the size of the field. And the tube, it's putting 2 plates, you put a collimator like that, horizontal collimator, which means the particle goes straight up, they bend. They're going to go through here. To go through, you have to start first to the right, and then you turn, basically, you go to the slits, and you get to the film to the right or the left, depending on the size of the direction of the magnetic field. It turns out the bending depends on 3 parameters. It depends on the mass. If it's very heavy, it's difficult to bend. Depends on the charge. More charge you have, more bending you have. And on the velocity. If you go very fast, you don't bend very much. If you go very slow, you have more time to bend. So Rutherford did 2 experiments, one magnetic, one electric, from which you can get rid of one unknown, the velocity, but you're left with 2 unknown, the mass and the charge. So you could not measure at the time the mass or the charge. You could measure only the ratio of the 2. So it's written here. He measured the ratio of the charge to mass to be 5.00, that's a unit. From which he concluded, and that's in the paper, Rutherford concluded that the alpha particle was probably the doubly charged atom of helium. It's interesting you read that, because today we know it's a nucleus of helium. But he could not talk about nucleus. This is 10 years before he discovered himself the nucleus. But they knew about charged atom. They knew since Thomson basically that if you have an atom of helium, you can take electron out. You're left with the negative atom. What's left behind, the positive atom. In fact, if you take negative electron out. So that's why he could say the data are consistent with doubly charged atom of helium, in which I took 2 electrons out. We cannot prove that because you can double the charge, double the mass, and still have the same bending. It took another 10 years because he could prove that the alpha particles were really helium. This desk is the desk of Rutherford at McGill.
Oh, wow.
It has an interesting story that if you close it, it's broken here. And the reason it's broken is that when they transformed the physics department into a library, they cleaned the place. And they found out the top of Rutherford's desk was radioactive. So they cut the top of that and they changed that panel also, but they kept the desk.
Is so much radiation that it was dangerous, you think?
No, and I took care, I was director of the fossil lab when they turned on the cyclotron, when they closed the place. So our company went around with a Geiger counter and checked basically. There was a room which was called, I forgot how it's called, where they prepare sources. And there was radioactive spot everywhere. Scientific equipment, roughly between 1850, 1920. There's something more modern, there's something older. The oldest thing we have here is this book here. This is Optics by Newton from 1704, the original. It has been bound, but the paper is original. So it's written 1704. Wow. Somebody wrote Isaac Newton, but the original book doesn't know that. In fact, if you go to the Google and you read about optics in Google, it's written that Newton didn't put his name on the front page, which is very strange. It's in English, it's easy to read. You can download it and read it. And in fact, what's interesting is that the third quarter of the book at the end is about calculus. There was a fight at the time between Leibniz and Newton. Leibniz had invented calculus. Newton said, no, I did that 30 years ago. But he never published it, so he decided he should publish it. So he put it as an appendix to this book, even if it has nothing to do with it. In the next edition, it appear. And not only that, what's interesting is that the calculus section of that is in Latin. This book is in English, but the calculus section is in Latin. So it's full of various scientific equipment. Sometimes it's related to real research. Sometimes it's about teaching that you can use in a very old projector, in fact. And they had some mechanics on it, for example, and so on. So it's kind of a mixed bag of a very important thing. At some point around 1880, in fact, instead of using prism to do spectroscopy, they use what's called grating. Grating is a piece of metal in which you scribe basically a very thin line spaced roughly by a wavelength. And if you send light to this grating, the reflection of light, each wavelength would reflect at a different angle, roughly. So you use that as a spectroscope, basically, very much replacing a prism, in fact, in trying to measure wavelength of light, in fact. What else? In fact, this I was writing about it yesterday. It's called a phonograph. to measure the speed of sound, in fact, half a millisecond. It was given to a company called Bergman to produce 200 of them. There's 104. The recording was done on a sheet of tin. The way it works is that you talk here, it vibrates the plate, it vibrates the needle. You rotate that, it's follow a screw here, follow the groove there, and everything moves. And so you talk here, it vibrates the needle, but you roll a sheet of tin here. It's called a tin phonograph.
I've seen some of those in museums.
Yeah. So basically what you have here is that you would have basically your needle that vibrate on the sheet of tin, which is above the groove. So the groove is just to give you space. And to play it, you go back to the beginning. And in fact, what Edison really invented is a way to play it. You reduce the pressure, so the needle will follow the tin. You produce sound. Except I was told that if you play it at the time, you will get a raise after 2 or 3 times. Every time you play it, you erase it. In fact, I was reading a text about all recording, and the text state, in fact, very interesting, that there was a period of time, this time, around 1880, where the kids, they talk about a quiet time, that basically library who had recording of that time could not play them, because in playing them, they erased them. So there's a quiet time where basically, it's not you don't have to, you cannot listen to it. It turns out, and I finish on that, to say, the first recording of sound was done 20 years before that, in France. It's on the web, in fact. Or YouTube, you can see first recording of sound is there, by Mr. Schmidt. And it's the same logic. You talk to something and you have a needle that vibrates. Except at the time, the recording was on a piece of paper. So you have a needle, on top of a piece of paper, put some ink, and you pull the piece of paper, that follows basically the trace.
I don't know how I would play it back.
You got it. They could not play it back. You can study the trace, you can study frequency, that is, you can study sound, but you cannot play it back. It took 100 years to play it back by physicists. In fact, physicists in Berkeley, among other things, but it's on the web, said, wait a minute, no, we can play it back. You take a picture of the trace with your computer, and then you get a computer to follow the trace. They did exactly that. And said the first recording they did, the first time they listened to it, it was too high frequency, it was too high pitch, it was, and they said, oh, wait a minute, we don't know at what speed you put the paper. They made a factor of 2 mistake, it seems. So they adjust the frequency, they adjust the speed to be more natural frequency. I listened to it, it was, this is a joke. They hadn't done anything. So I read the text, and the text said, there's one paragraph of text said, the guy is singing, is Mr. Schmidt. It's in French, it's called Mr. Schmidt. The guy is singing Au clair de la lune. If you know Clair de la Lune, it's a French song, it's a French kid song, in fact. I listened to it, he is really playing Au clair de la lune. You recognize it, question about it. This is various X-ray tube. McGill was, in fact, if you look at the photo there, which is also in the entrance of the building, McGill was McGill did one of the first 2 X-ray pictures taken in North America. The other ones from Dartmouth College, in fact. So they were using this type of tube. These tubes, some of the more modern one is from 1950. The X-ray tube was used by doctor. These are oldest from turn of century type tube. This is interesting too. This was a Marconi wireless telegraph. This box was designed by Marconi in 1902. This box itself is from 1905. And in fact, the idea is that you have a cable here. The cable is made out of a small piece of iron filing. So you have a spindle here, you turn the cable. You use this magnet to magnetize the cable, make a small magnet. Here, next somewhere, because it's very symmetric. You connect that to the antenna on the boat. On the ground, you can use cable between city, but not on the boat. You have to use wireless. So the wireless wave coming to the boat to an antenna on the boat, produce a current. You send the current here. The current will send a coil, you will demagnetize the cable. And here the third person will be listening to the cable. For example, there is here. This is a photo of the radio office of the sister boat to the Titanic, when they made a copy of the Titanic. And this guy is listening basically. And if you receive a radio wave, you change magnetization, so you will hear so it fluctuates. And it works like that from 1902 to 1908, which means that this has no way to separate two radio waves. So you receive two radio waves from two cities on the ground, you're stuck. It's in 1908 finally that there was more and more radio waves that Marconi invented. I called it a tuner, so it's not called, I forgot what it was called. Is this box. This box is a filter, it's just a filter. It just, there's no transistor in that. So it's pure, it's a RL filter or RC filter to adjust frequency. Mm-hmm. It's like various in the old radio. You have a knob, change station. Change station is what? You change the frequency you receive. And like I tell people in general, your cell phone, when you have there, is not different than that.